Let's see if that works now. Right. Wait, we lost your. Okay, that should be nice. All right, great. So next we have a contributed talk from Jisu on adaptive visual abstraction by object token merging and pruning for efficient robot manipulation. Yeah, you can start whenever you're ready.
Yeah, thank you. Today I want to present about adaptive visual abstraction via object token merging and pruning for efficient robot manipulation. Oh, okay. So I want to start with the motive of language-driven household manipulation. So language has the potential to serve as a powerful communication channel between humans and robots in home, workplaces, and industrial settings. So if you see the figure in the right, as in the left figure, you can see the Samsung robot doing the household chores. And I believe the most efficient way to communicate with these kinds of robots would be ultimately will be the language. So to considering this practicality, recent papers led the robots to perform tasks given in natural language, and specifically in the vision-based imitation learning. So, however, these would be the current examples. So the language following requires not only recognizing the task-relevant objects from the visual scene, but also identifying the constrained objects that could potentially influence the task performance. On the left side, you can see the user prompt, which is to open the top drawer. And on the scene, there is a Franca Panda robot trying to reach to the drawer and then to execute the task. But if they do not recognize the constraint object, which is the base, it will ultimately result in the task failure. And these kinds of things would be due to the lack of awareness of obstacles within the robot trajectory. So to address this, recent studies like Fox Poser in the robotics field has included the constraint objects directly in the input. So as you can see in the left figure, they also add, please also watch out for that phase. But these kinds of specifications in the real world would be very problematic because it lacks the practicality. So one of the possible solutions would be leveraging the VLM models. So for example, we can use the fetch clip information. So given the
Mind or
our selection is good.
So tries to focus on the robot itself, but not on the constrained objects that is the notebook on the scene itself. And also, we can also use the VLM models such as grounding dyno by asking necessary object segments directly. For example, given the image and the prompt, which is giving some information that the model is the Franca Panda robot and we have to perform the task and come up with a list of object segments. We can also fetch the relevant objects, which would be the robot body and oven knob. But while the robot is trying to perform the task, it might need to consider the constrained objects, which is the gray colored, but they cannot identify them. So to leveraging VLM models would also be a possible solution, but since the VLM is not conditioned on the robot configuration, and this would be due to the lack of reasoning about how the robot operates at the motion level and what should be considered as constraints. And these kinds of schemes would be ultimately result in task failure. For the second possible solution, we can also considering fetching all object segments. So for the robot to perform in the multitask manner, they usually need to fetch the fine-grained level of segments so that they can handle a multiple tasks. So for example, given the image, and if we like want to open the oven, they have to focus on the oven knob. And if they want to turn on the oven, they have to focus on the oven buttons. And to consider these kinds of different details of segments, we have to fetch the fine-grained level of segmentations, like as presented on the right. So if you like want to consider the fine-grained levels of objects, and it would be different each scene, we have to use the transformer-based architecture. And as the left figure, as you can see, each segment can be encoded as a token, and then this would be a huge amount of tokens in the real world. But processing them using transformer-based models would incur significant computational cost. And this is usually because of the quadratic time complexity of the multi-head self-attention, and this will make the real-time operation really challenging for the robot. So I believe balancing the computational cost and the number of object tokens should be problematic as it goes to the real world. So our goal is to enable the efficient robot manipulation through visual abstraction. Given the task and the image, rather than using the fine-grained segments, we want to fetch only the goal-oriented segments that would consist of task-relevant objects, which would be the oven knob, and also the constraint-relevant objects, which would be the constraints that might hinder the task performance. And by doing so, we also want to maintain the success rate and also ultimately reducing the computational cost. So to solve this, our approach relies on the human intuition. So usually humans to perform the given task, which is trying to fetch the red layer book, which is layered on the upmost side. Humans automatically merge the relevant objects required for the task to proceed and prune down the objects that are not relevant for the task. So we automatically merge adjacent objects as a single constraint related segments and also ignore the non-related objects. And we want to realize this intuition by token merging and pruning. So when given the very abundant number of tokens, by utilizing object token merging and pruning technique, we want to reduce the number of token size, which would be ultimately reducing the computational cost. And also, since the relevant properties are only left, the performance can be maintained too. And this would be the basic plain block, which you can see on the left figure. But instead of using this transformer basic plain block, we use the merging and pruning block that coexist in the different order. So starting from the mass token of 20, by passing each blocks, it would reduce into a small amount of blocks, a small amount of object tokens. So on the merging block, it tries to group the tokens that take the same meaning in order to accomplish the task. So by passing the multi-head self-attention process, the tokens that may exhibit in this high cosine similarity would be grouped in and merged into fewer tokens by using the weighted sum based on the attention scores. And also on the pruning block, we try to use this pruning block because the meaningful grouping will not occur if there is no additional explicit tools. So to facilitate the meaningful grouping, we use the pruning block, and this could be done by using the attention scores between the goal and object token to identify and remove the top K tokens with the lowest relevant scores. Under this block architecture, I also want to present the model architecture too. So we utilize this intuition under the vision-based imitation learning. So starting from the environment, we fetch multi-view images, which can be the middle right, the front and the wrist information. And we fetch the segmentation by utilizing the foundation models. After encoding the object encoder, then we use the object token merging and pruning for each view. And when the object tokens are reduced, we pass the translation head, rotation head, gripper head, and then finally conclude the next action token for the next action for the robot, which would consist of translation, rotation, and gripper state. So on the experiments, we want to investigate the following questions. Does our model generalize better compared to the models that not use or like using foundation models? Or does our model is more computationally efficient? Or do we really need both merging and pruning techniques? For this, we evaluate with the success rate and the computational cost. And the baselines would be consist of mostly two. So first is about the different task relevant object information from CLIP or VLM. And we also utilize different configuration of merging and pruning blocks. So we test our hypothesis on the articulated object multitask robot manipulation. We test on RL bench 6 task, which is open grill, close grill, or turn oven on, open oven. And the reason we chose this domain is because the object information requires differs depending on each task. And this also happens when manipulating same articulated objects for different tasks. So as you can see on the right figure, for the robot to execute the turn open on or open open, they try to focus on different points, which would be the open button or open up. And we wanted to check whether the robot focus on these kinds of different points. That depends on the different tasks. And also the challenging task, where we use the constrained objects, which includes 3 or 4 unseen distractors. So for the quantitative results on the success task, we compare the success and the rank of the average task. And as you can see, GOS, our model outperforms compared to other models. And also integrating merging and pruning blocks, our model show more higher success rate than others, showing that we have to use both merging and pruning blocks to ultimately achieve the task. So I also want to show you the qualitative results. So we compared with we visualize have to identify the shelves that are in brown colored, and VLM guided segments take hard time identifying these kinds of constrained objects, and this will ultimately result in task failure. And also to open the grill, they have to focus on this grill point, and also considering the constraints that are around in their area. But also we can see the VLM guided or segments also fail, and also fine grained segments trying to fail this scene. We also finally want to report the computational cost. So here the G-flops are the computational cost that is calculated, and the diffmin is the column that is divided by the minimum value. And as you can see, GOS is significantly more cost effective than both VLM and SAM. So for the conclusion, we propose a model that tries to incorporate the visual abstraction into object-centric representations by selectively merging and pruning object information. And our work empirically show that our method is significantly more efficient in terms of performance and computational cost. Yes, this is the end of my presentation, and thank you for listening.
Yeah, thank you very much. Are there any questions? Perhaps a quick one for me. So I'm not sure if I missed it somewhere, but have you also tried transfer learning between tasks? Like what happens? Can you share between tasks, or is it like relevance in one task is the focus, and that's it?
Can you elaborate again? I actually did not.
Go into your conclusion slide.
Yep. Yes.
So, so you prune object information based on the relevance and the importance to the task. But what if there are multiple tasks that are relevant? Does pruning still work? What if the tasks are sequential? Does this matter at all, or not really?
So for different tasks, they try to focus on different segments. And in the sequential, we did not test it on the sequential manner, but it would be also worth trying if you want to expand this work.